Hi, I'm Ms. Roger, and welcome back to Core Concepts in Algebra 2. Today's lesson is on complex numbers. The Massachusetts curriculum frameworks for mathematics are tied to this lesson, specifically N-CN, number and quantity, the complex number system, number 1 and number 2. Let's take a look at the lesson objectives. To define a complex number, to evaluate negative values under the square root symbol, to evaluate powers of I, and to perform operations with complex numbers. Let's take a look at the mathematical definition of a complex number. A complex number is any positive real number written in the form a plus bi, in which we have a real component and an imaginary component. For a plus bi, our real component is going to be our a value, and our imaginary component is going to be the bi value. The imaginary number I is defined as the square root of -1. Let's take a look at some problems. Let's take a look at simplifying radicals with negative numbers under the square root. So I want to think about radical -36 as radical -1 times radical 36. Radical -1 is I, which is our imaginary number, and radical 36 is going to be 6 times 6. It's a perfect square, so it's just going to drop down to just be 6. So when I multiply these two values together, I'm going to get 6i. This is simplified for radical -36. For radical -40, I want to think about the same ideas. What times what is 40, -40 specifically. So I'm going to think about this as radical -1 times radical 40. Radical -1 is I. And now I want to start to split up radical 40. So if I can think about a combination of two numbers that multiply together that are 40's factors, preferably one being a perfect square, then I can break this down. Radical 4 times radical 10 is radical 40. And radical 4 is 2. Since it's a perfect square, 2 times 2 is 4. And radical 10 does not break down. So when I put all of my circled terms together using multiplication, I'm going to have 2 times I times radical 10 to give me 2i radical 10. And I want to break this down as simply as possible using this idea of square roots in perfect squares. So if I think about radical -32, I'm going to do the same idea. Radical -1 times radical 32. Radical -1 is I. And radical 32 is going to be radical 4 times radical 8, because 8 times 4 is 32. Radical 4 is 2. And I can keep going. So when I can keep breaking this down, that means I didn't pick the biggest perfect square that goes into it. So radical 8 is going to be radical 4 times radical 2. Radical 4 is 2. And the square root of radical 2 does not break down. And as you can tell, you really have to account for each step of this. So at the end of each one of these branches, when I'm done, I like to circle it to help indicate kind of where I'm at. So I'm going to multiply all the circled items. 2 times 2 is 4, times I is 4i, times radical 2. So my final answer for the square root of -32 is 4i radical 2. Let's take a look at another multiplication problem with complex numbers. So radical -4, again, I want to think about as radical -1 times radical 4. And when I use the word radical and square root can be used interchangeably, so please be aware of that. Radical -1 is I, and radical 4 is 2 since it's a perfect square. So if I think about radical -4, this breaks down to simplify just to be 2i. Okay? I'm going to deal with each one of these components separately and then put them back together at the end. So I'm going to bring my times symbol down, and now I'm going to deal with -2 radical 16. So we do want to review our perfect squares if we have a chance, and be aware of what the perfect squares are and have those ready to go. Radical 16 is a perfect square, and it is 4. So I'm going to think about radical 16 as 4, and I can multiply it by the constant in front. So 4 times negative 2 is going to give me negative 8. Since I've split both of these up and worked each one out separately, I'm now ready to multiply. Negative 8 times 2 is going to give me negative 16i. So I can put square roots together that have negative numbers under the radical and simplify down to one value. Let's take a look at another problem that's a little bit more complicated. Radical negative 18 times radical negative 24 times 4 radical 2. So let's start and just go left to right and deal with each one separately. So radical negative 18 is going to be radical negative 1 times radical 9 times radical 2. So radical negative 1 is I, which if we want to just pull out an I immediately and make it a positive 18, we can do that. Radical 9 is a perfect square. It is 3. And radical 2 does not break down. So as you've noticed, I've been using this tree branch method. And when I get to the end, I circle it. This is just one way to stay organized when you're working through this. 3 times I is 3i times radical 2. So radical negative 18 is 3i radical 2. We're going to bring down our times sign. Radical negative 24. So again, I'm going to just immediately pull out an I and show you that way. So I'm going to think about this as I radical 24. And right off the bat, I'm going to circle my I, and I'm going to think about radical 24 now. This is another way to think about it now that we know that we can pull out that I. So 24 is going to give me 6, 12, 18, 24. 6 times 4. Radical 4 is 2. And when I think about 6, I think about the factors of 6, 3 times 2. Neither of those are perfect squares. So that's going to be circled. Now I take all the circled terms and I multiply them together. 2 times I is 2i radical 6. Okay? So I'm slowly but surely getting more terms here. And let's deal with the last one, 4 radical 2. When I look at that, I can't really do anything. Radical 2 is not going to simplify, and then I just have the 4 being multiplied by it. So this is just going to come down, times 4 radical 2. So now that I've simplified each one separately, now I want to deal with the like terms. So my 3i, my 2i, and my 4 are going to be multiplied together. So 3 times 2 is 6. 6 times 4 is 24. I times I is I squared. And now the value under the radical. Radical 2 times radical 6 times radical 2 is going to give me radical 24. And at this point I need to kind of keep going. I need to keep simplifying. So this value of I squared is negative 1, which we're going to talk about in a few minutes. So I'm just going to tell you that. So 24 times negative 1, radical 24, is going to give me negative 24. Radical 24. We're going to think about this idea in the next problem. But for right now, let's just accept it to be negative 1. Radical 24 can simplify, which we saw above. It's going to be radical 6 times radical 4, or radical 4 times radical 6. Typically, you put the one with the perfect square first. So this is a value of 2, and that stays. So now I can continue to combine like terms. So I'm left with negative 24 times 2 radical 6, which is going to give me negative 48 radical 6. So this is my final answer for this problem. Let's take a look at powers of I. So in the previous problem, I told you that I squared equals negative 1. This is a fact. We also talked about in one of the previous slides in regard to the definition that I to the first equals the square root of negative 1. So if I think about other powers of I and how I can build this, I want to ultimately be able to think about now I to the third power and I to the fourth and so on and so forth. So if I think about how I can build to this just using I and I to the second, I can think about this as I times I to the second. Because when you have the same base, you can add the exponents. So 2 plus 1 is going to give me my 3. So if I think about what these values actually are, I squared is negative 1. When we think about I as being the square root of negative 1, this is just a fact. We're not going to replace I with the radical negative 1. We're going to keep I as it is. But powers after that, you are going to simplify. So when I think about I to the third, if I'm going to finish this off, I is going to stay as I, and I squared is negative 1. So I times negative 1 is negative I. So I to the third is negative I. And that's how we can build this. Let's look at I to the fourth. Again, we can think about this since we're in base I. We can think about this as I squared times I squared, since we can add the exponents using our exponent rules. So I to the fourth is going to equal I squared is negative 1. Negative 1 times negative 1 is going to be positive 1. So I to the fourth is 1. Let's keep going. I to the fifth, we can think about any combination of this. So why don't we do I to the third times I to the second. 3 plus 2 is going to give me my 5. So we know what I to the third is. We know what I squared is. I to the fifth equals I to the third is negative I, which we proved. And I squared equals negative 1. So I to the fifth equals negative I times negative 1 is just I. Let's look at I to the sixth. I to the sixth, we can use I to the third times I to the third. 3 plus 3 is 6. So I to the sixth is going to equal negative I times negative I. So I to the sixth is going to equal negative and a negative is a positive. I times I is I squared. So this probably wasn't the best combination because we have to keep going. I squared is negative 1. So I to the sixth is negative 1. If we keep going, I to the seventh is going to equal I to the fifth times I squared. And try and make sure when you are doing these i's that they don't look like ones. Try and loop the I a little bit. I to the seventh, I to the fifth, we got to be I. And I to the second is negative 1. So I to the seventh equals negative I. We want to look at this and think about if there are any patterns happening. So if we look at I, we start with I, and our I to the second is negative 1. I to the third is negative I to the fourth is 1. I to the fifth is I to the sixth is negative 1. I to the seventh is negative I. What do we think is going to happen for I to the eighth if we look at what's going on? Is there a pattern? And yes, there is. Every time we get a cycle of 4, it repeats. So I to the fifth was I, then we went to negative 1, then we went to negative I. So we should end up with 1 here if this pattern is correct. So why don't we see? Why don't we do I to the seventh times just I. 7 plus 1 is 8. I to the eighth is going to equal negative I times I, which is going to be I to the eighth equals negative I squared. I to the eighth equals I squared is negative 1. So this is negative times negative 1. I to the eighth equals 1. And that's what we thought it was going to be. So this pattern keeps happening. And we're going to use this pattern to find additional powers of I. So when we're thinking about patterns of I, there's another way to think about this process. Since we know it's cyclic, which means every time we get to a power of 4, it repeats, we can think about when we have large powers of I using what the remainder would be. So we can simplify powers of I by grouping. We can figure out how many groups of I to the 4th there are in a number, and then think about what's happening with the remainder. So we're going to look at this in the next problem, but if the remainder is 0, the answer is 1. Would be as if we had I to the 0 power, which is just 1. If the remainder is 1, the answer is going to be I, because we're going to think about this as I to the 1st power. If the remainder is 2, the answer is -1, because we're going to think about this as I squared, which is what I squared is. And if the remainder is 3, the answer is going to be -I, and we're going to think about that as I to the 3rd. So this is when we have large powers of I. We're trying to figure out what the value is. Ultimately, our options are 1, I, -1, and -I. Let's take a look. So let's take a look at what we just did. We have I squared equals -1, I to the 3rd equals -I, and I to the 1st equals 1. If we think about I to the 22nd power, we're not going to build our values of I every time. We want to have a fast method to figure out powers of I that are greater than, say, 8. If I think about 22, I want to think about how many groups of I to the 4th go into I to the 22nd. So I can take 22 and I can divide it by 4 and see how many times it goes in. So I'm going to think about this as 5 groups of I to the 4th. 5 groups of I to the 4th. So 5 times 4 is 20, and my remainder is 2, with I to the 2nd remaining. What's remaining is what I'm going to evaluate. So I squared equals -1, so I to the 22nd equals -1. If I think about I to the 32nd power, I'm going to use the same process. How many groups of I to the 4th go into the I to the 32nd without going over? Whatever the remainder is going to be my answer. So 8 groups of I to the 4th. 8 times 4 is 32. So we have I to the 0 remaining. And if we think about the previous slide, I to the 0, anything to the 0 power is going to be 1. So I to the 32nd power is 1. Let's take a look at I to the 51st power. How many groups of I to the 4th go into I to the 51st without going over? 12 groups. Twelve times 4 is 48. 51 minus 48 is going to be I to the 3rd remaining. I to the 3rd is -I. So I to the 51st is -I. Let's look at I to the 70th. How many groups of I to the 4th go into I to the 70th? 17. With I squared remaining. I squared is -1. So I to the 70th is -1. For I to the 96th, this is going to be 24 groups of I to the 4th with I to the 0 remaining, which is going to be a value of 1. And our last one, I to the 101st power, is going to be 25 groups of I to the 4th with I to the 1st remaining. So our answer is going to be I. We can extend this to higher powers. We can look at I to the 800th power and so on and so forth with just thinking about how this pattern repeats. So we'll think about this more tomorrow, and we're going to use these facts for additional problems. Let's take a look at a problem using operations and multiplication with complex numbers. So I have 2 plus I and 7 plus 4i. Notice that these are in a plus bi form. What we're going to do is we're going to multiply these two numbers, these two complex numbers together, and hopefully get another complex number, but let's see what happens. So I like to use the FOIL method, first, outer, inner, last, which ultimately just multiplies everything in the first by everything in the second. So let's use this. 7 times 2 is 14. 4i times 2 is our outer two terms, is going to give us 8i. Our inner two terms are inside. 7 plus I is 7i. And our last two terms, 4i times I, is going to give us 4i squared. So our next step is to simplify, combine like terms, kind of work this out however we can. The O and the I of FOIL is always going to combine together. They're always like terms. So we have 14, 8i plus 7i is going to give us 15i. And we have our plus 4i squared. What we just learned from our previous problem is I squared equals -1. This is a fact we're going to use over and over and over again. So keep this in mind when you're working. I squared equals -1. So I have 14 plus 15i plus 4 times -1. I'm replacing I squared with -1. So this value right here is going to become -4. So I have 14 plus 15i minus 4. My like terms now is my 14 and my -4. 14 minus 4 is going to give me 10 plus 15i. This is my final answer. It's in A plus BI form, where 10 is the real part and 15i is the imaginary part. And notice when we multiply two complex numbers together, we get another complex number. Let's take a look at another problem. Simplify -1 minus 9i all squared. What this squared is going to mean is that we're going to have to write -1 minus 9i twice. So we're going to write -1 minus 9i times -1 minus 9i. Now we're going to do what we did in the last problem and multiply the two binomials together. So we're going to FOIL. First, 1 times 1 is 1. Outer, -1 times -9i is positive 9i. Inner, -9i times -1 is positive 9i. And our last is -9i times -9i, which is going to give us a positive 81i squared. Notice that I squared is coming into play again. So we can combine our O and our I of FOIL. 1 plus 18i plus 81i squared. We can evaluate or simplify I squared because I squared equals -1. Don't forget that fact. So 1 plus 18i plus 81 times -1. So we get 1 plus 18i minus 81. And now we can combine our 1 and our -81. 1 minus 81 is going to give us -80 plus 18i. Again, notice we go from two complex numbers to our result. Our answer is another complex number. Let's take a look at another problem. This time we have 3 complex numbers being multiplied together. So we can handle it a similar way. Now we're just going to have to deal with these two first, FOIL them out, get a complex number, and then multiply our answer by 1 plus 8i. So let's do that. Let's FOIL the first two complex numbers, get another complex number, and then multiply it by 1 plus 8i. So let's do the similar process. can't think. Is this 14? 14i plus 14i plus 8 times plus 14i minus 8. So now, when we multiply our first two complex numbers together, we get a result of negative 23 plus 14i. We're going to take our result, our answer here, and multiply it by 1 plus 8i. So let's do that over here on this board. So when we multiply negative 23 plus 14i and 1 plus 8i, and we use the same process and the same steps from the previous two problems, we get a new complex number, which is our answer, negative 135 minus 170i. Let's take a look at another problem. 8 all over negative 1 plus 2i. Similar to how we don't like radicals in the denominator of a fraction, we also don't like complex numbers in the denominator. So in order to produce a denominator with a real number, we multiply by what's called the complex conjugate. What that is when we multiply by whatever's in the denominator, negative 1 minus 2i all over negative 1 minus 2i. So what the complex conjugate does is it takes whatever sign is connecting the real part and the imaginary part, and it changes it to the opposite. So notice we went from plus to minus. Negative 1 minus 2i all over negative 1 minus 2i is a value of 1. So technically, if we multiply 1 by this number, we're just making it look a little bit differently, which is ultimately our goal. So what we're going to do here is we're going to do multiplication, 8 times negative 1, 8 times negative 2i, and then multiply the two complex numbers in the denominator. What this is going to do for us is get us a real number in the denominator, which is ultimately what we're after. So let's do this. 8 times negative 1 is going to give me negative 8. 8 times negative 2i is going to give me negative 16i. I think about this as like the distributive property. And now I'm ready to multiply these two complex numbers in the denominator, similar to what we've already been doing. So when I FOIL and multiply the two complex conjugates in the denominator, I end up with this. Notice how the O and the I of FOIL are going to cancel out. That's the whole goal. This is going to happen every single time. Our I squared is going to evaluate to be negative 1. So again, we're going to get negative 8 minus 16i in the numerator all over 1. This cancels out. Negative 4 times negative 1 is going to give us a positive 4. So 1 plus 4 is going to give us our 5. So we have negative 8 minus 16i all over 5. And if we can simplify, reduce anything, we do. If we can't, we're okay to leave it like this. You can either leave the answer like this, or you can write this in a plus bi form. So if I think about this in a plus bi form, I think about negative 8 all over 5. This is the real part, plus negative 16i all over 5, which is the imaginary part. Both of these answers are correct. And this is how you rationalize the denominator with complex numbers. Let's take a look at another problem where we use a complex conjugate. So let's multiply by 3 plus I. This technically, remember, is a value of 1. This is the complex conjugate. So we're going to now multiply the two numerators together using the methods we already talked about multiplying complex numbers, and multiply the two denominators together, and then simplify whatever we can do. So when I do that, I get this in the numerator and this in the denominator. Now it's time to simplify, combine like terms, evaluate I squared equals -1. So let's do that. So my final answer is going to be -17 plus 11i all over 10. Or if I want to write this in a plus bi form, I can say -17 all over 10 plus 11i all over 10. Both of these are solutions. They're the same thing. It just depends on how you'd like to write them. So we've looked at multiplication and division with complex numbers. Now we're going to take a look at addition and subtraction. So we have one complex number and it's being subtracted by another complex number. What we're going to do is we're going to take the real components and subtract them, and then we're going to take the imaginary components and also subtract them. So it's pretty straightforward. -1 minus 4 is going to give me -5. Those are both the real parts if I think about a plus bi and a plus bi. And then I can take -2i and subtract 10i to get -12i, which is my solution. Let's take a look at an addition problem with complex numbers. Again, let's add the real components and add the imaginary components. So -3 plus 5 is going to give us a +2. And 6i plus -4i is going to give us a +2i. So our solution when we add these two complex numbers is another complex number, 2 plus 2i. What is the purpose of complex numbers? How are complex numbers represented, and where do we see them in mathematics? How do the rules for simplifying algebraic expressions apply to simplifying complex numbers? Think about these essential questions tonight, and we'll discuss them in more detail as we explore complex numbers tomorrow during class. After watching today's lesson on complex numbers, try these. Simplify each of the following problems. The first one is evaluating negative values under a square root. The second problem is dealing with large powers of I, so use your rules that we talked about. For the third one, we're multiplying two complex numbers. And for the fourth and fifth one, we're adding and subtracting two complex numbers. Thanks for joining me in Core Concepts in Algebra 2. See you next time.